Hi, I'm Hiran Sarkar and I'll be presenting our work NeRF, learning generalized continuous spacetime scene dynamics with Neural ODE-based NeRFs. Most dynamic scene reconstruction methods parameterize time as a discrete set of frames, or they learn deformation fields corresponding to each time step. Therefore, our motivation stems from two folds. Number one, previous scene reconstruction methods are constrained within the observed time steps and fail to extrapolate beyond what they see during training. For example, here we are given a scene of bouncing balls. Now, the previous methods would be able to reconstruct the scene within the observed time steps, but when they're asked to extrapolate, we observe disintegration of the scene, disappearance of the scene, or deformation of the scene. Our second motivation comes from a multi-sequence setup. Imagine we have a scene with multiple sequences of object motion. Sequence A with the dynamic object have one motion sequence. Sequence B with a different motion sequence. Now, if a model trained on these sequences is asked to generate a new motion sequence from an unseen starting frame, previous method failed to perform the task. This is because they learn deformation fields which are sequence specific and doesn't generalize to multiple sequences. We therefore introduce NodeRF that combines the continuous dynamics time modeling capability of Neural ODE with scene representation capability of NeRF. Imagine we're given a scene. From this, we choose the first frame and learn a latent code corresponding to the first frame. This latent code is passed to a Neural ODE which captures the dynamics of the scene. The latent code evolves through time and generates multiple latent codes corresponding to multiple time steps. The neural ODE therefore learns a continuous time latent trajectory. We sample one latent code and pass it to NeRF. The NeRF uses this latent code along with the 3D coordinate and viewing direction to render an image. We can also consider the first frame as if it is coming from a particular motion sequences, let's say sequence A. We can also have multiple of these sequences, for example sequence B, which also pass through the entire framework as sequence A, and also another sequence, sequence C, which can also be passed through the entire framework through like sequence A and B. This allows Neural ODE to learn a shared latent dynamics, which can help with if our framework is provided with the first frame of an unseen sequence, it would be able to generate the entire sequence. If we delve in deeper into the single sequence setup, we are given training frames where each time step the scene is captured from a random camera viewpoint. Therefore, the task is to interpolate between the observed time steps and extrapolate beyond the observed time steps. NodeRF starts by learning the first two latent codes corresponding to the first two frames in the training set. Those latent codes are passed through an encoder which learns a distribution of those first two latent codes. We sample one latent code from that learned distribution, which is then passed to a neural ODE. The neural ODE takes the latent code along with multiple time steps to generate multiple latent codes corresponding to each time step. The generated latent codes is passed through a decoder from which we sample one latent code. That sample latent code is passed through a NeRF which renders an image. That rendered image is then supervised with the ground truth. Here is a qualitative interpolation result. We show 5x interpolation, which means we're interpolating 5 frames between two consecutive frames of the training set. Here is a long-term extrapolation or 4x extrapolation qualitative comparison, where here we observe 4DGS disintegrates the scene, hex plane vanishes the scene beyond the training window. DNRF and motion GS generates implausible extrapolations, whereas NodeRF generates plausible extrapolation with the balls eventually comes to rest. For quantitative analysis, we focus on prompt-based similarity benchmark. Here we use two models. First, a X-clip model, and number two, lava video model. With the evaluation prop, does this video show physically accurate motion where the bounce amplitude gradually decreases with no sudden jumps and the white ground plane remains completely rigid and motionless without any shaking, wobbling, or deformation? We also use VBench benchmark with two metrics, motion smoothness and subject consistency. We observe that we achieve SOTA results compared to the baselines. Coming to the multi-sequence dynamics, Imagine we are given multiple sequences where in each sequence the dynamic object has a unique initial position and initial velocity. For example, sequence 1, the dynamic object or the ball in this case starts from P1 position and V1 velocity. Sequence 2 has a different initial pose and initial velocity, and all the way down to sequence N where the ball has a different initial pose and initial velocity. And the task is during evaluation, we are given an unseen initial pose and initial velocity, and the model has to generate the entire sequence. NeRF starts by positionally encoding the initial velocity and initial pose. The initial pose passes through an encoder and is concatenated with the initial velocity and a canonical latent. The concatenated output is passed through a Neural ODE, which also takes multiple time steps and then generates the corresponding latent codes. The latent codes is then passed through three distinct decoders. A velocity decoder, which outputs the predicted velocity. The predicted velocities are then supervised against the ground truth. DP, which is the pose decoder, which outputs the predicted pose, which are then supervised against the ground truth. And DN is the NeRF decoder, the output of which is added with a static latent. The output, the output of which gives the NeRF latent. The NeRF latent is passed through NeRF, which renders an image. The image is then supervised with the ground truth. Here is the this is a qualitative result of the multi-sequence setup. We focus on the we also provide the optical flow of the predictions, and we observe that our predictions are much more closer to the ground truth compared with the baseline. This is the results from another scene, and here also we observe that our results are much more closer to the ground truth compared to the baseline. This is the quantitative results of the multi-sequence setup. We focus on the dynamic part of the results. Here we measure the IAU overlap between the ground truth and the prediction optical flows. Here is the optical flow representation of the ground truth. We observe that the flow of NeRF prediction closely resembles the ground truth, whereas the baselines generates noisy optical flows, which results in poor IAU overlap with the ground truth. A strength of NeRF is that we can plot the learned dynamics in 2D space using the learned latents. This is the latent space visualization of the bifurcating hill scene as shown on the left, along with the divergence plot. The green points represent the point in the scene where the ball is at the top of the hill, while the two sinks in the latent space with low divergences represents the two distinct scenes where the ball comes to rest. We apply Lipschitz regularization on the NeRF linear layers, which is basically a scaling factor to enhance the dynamics learning across multiple sequences. We observe the latent space without and with Lipschitz, and the one with Lipschitz provides a much more cleaner learning of the dynamics. Conclusion: NeRF augments NeRF with the predictive capability of Neural ODE. They learn the physical dynamics of the scene that can be temporally extrapolated. NeRF generalizes to multiple sequences and can generate novel sequence under unseen initial conditions. The learned dynamics is directly placed on the Neural ODE, which allows for latent space visualization of the learned dynamics. Please visit our project page and code for further details. Thank you.